Hi, it's Peter from Teach Me Maths. The topic today is going to be arithmetic sequences and mainly working towards the proof of the sum of an arithmetic sequence. If you're doing first year A level, many of you will have seen the formula for the sum of an arithmetic sequence, and maybe you wondered where it came from, maybe you didn't, but there are some past exam paper questions that do ask you to do the proof, so it is an important topic to cover. Before I go straight into the proof for that, I think it's worth actually looking at arithmetic sequences, understanding what they are, and also getting our head around the notation that we use for sequences, and then the proof should be a little bit clearer. You might be wondering why this fella Carl Friedrich Gauss is on the screen. Basically, this guy came up with the proof for this, and he came up with a kind of technique for basically adding up a lot of numbers, and as long as those numbers are in a sequence. Okay. Now the impressive thing is, I mean, this guy was extremely impressive. He was born in the 18th century, and he made a lot of contributions to maths and physics. This topic that we're covering came up with when he was about 10 years old. So obviously he was showing signs of being a bit of a genius already at that age. Okay, so I would encourage you to maybe sort of look into Gauss and have a look at what his contributions to maths and physics were. But really the point of mentioning him was that this technique came from a 10-year-old. Okay, so let's have a look at what he did. So we'll just go to the next screen. Okay, what he was actually asked in school was to add up the first 100 natural numbers. So natural numbers are just the counting numbers. So you can imagine kind of writing out 1, 2, 3, 4, 5, and trying to add those up all the way to 100. So it's pretty easy to start with. 1 plus 2 is 3, plus 3 is 6, 10, 15, 21, 28, etc., etc. But it then just starts to get more difficult. It's easy to make a mistake, and it's just long, boring, and tedious. Okay, so when he was asked to try and do this, he tried to explore things and trying to see whether there's a clever technique. Now what I'm going to do is I'm just going to kind of put a ... in there. These numbers obviously carry on, and then I'm just going to write the last few numbers in. Fairly obvious here, but this is going to be important when we do the actual formula later on. Okay, so he kind of looked at these numbers and he decided to basically write the numbers backwards. Okay, underneath. Okay, so 98. Okay, ... and then the last few would be 3, 2, 1. And what he noticed, that if you add these together, you basically get the same number. Okay, 1 plus 100 is 101. Okay, 2 plus 99 is 101. Okay, and these are all 101. And once he realised that, it made it a lot easier to add these up, because basically we're adding these numbers up, but they're all the same number. So if you take a minute just to think about this, it's fairly easy to see how many we've got. There would be 100 of these. Okay, so the sum of this would be 100 times 101, which of course is nice and easy because we just write down 101 with 2 zeros on the end. There's one more step. You've just got to think, hang on a second, we've written those bunch of numbers twice. Okay, so in effect, what we've done is we've added the numbers from 1 to 100 and then from 100 to 1. So basically, it just means that this is 2 times too big. So if we divide it down by 2, we're going to get the correct sum of the first 100 numbers. Okay. The next step really with this is to realise that there's nothing particularly special about 1, 2, 3, 4, 5 up to 100. This will work with any bunch of numbers as long as they are evenly spaced. Okay, so I'm going to pick maybe 2, 7, 12, and I'm going to carry that on. Okay, and the reason that I know this is going to work is because it is an arithmetic sequence. So what do we mean by arithmetic sequence? Well, it just means that the numbers are going up by the same amount. So 1, 2, 3, 4, 5 is going up in ones. This is going up in fives. Okay. Now what I'm going to do here is kind of just try to show you something slightly different that will maybe help you see why this works. Okay. Let's say we were just going to add these 3 numbers up. Okay. Now obviously the quickest way to do that is to just look at the numbers and add them up. Okay. So we've got 3 numbers there. 2 plus 7 plus 12 is 21. Okay, the way I kind of see this is that if you look at the 7 in the middle, you've got one number to the left that is 5 less, and then you've got one number after it that is 5 more. Okay, so I kind of think you can almost balance this out and say the sum of these three numbers is going to be the same as adding 3 7s together. It's like the 7 is the average of those three numbers. So then I would do 3 times 7 and still get 21. Okay, and this would work with any amount of numbers. It's easier when there's an odd amount of numbers. So let me just give you another example. 1, 4, 7, 10, 13. Okay, if you look at that, the middle number is the average here. Okay, so I know that the sum of these numbers is 35 because it's 5. I've got 5 numbers. The average is 7, so I treat it as if it's 5 lots of 7. Okay, now you can check that if you like. You can pause it, add those numbers up manually. You should get 35. Okay, so let's just go to the next screen. It will work a little bit differently if you've got an even number of numbers. So let's do another sequence. Let's say that we were adding these 4 up. Okay, well now the average sits in between 5 and 9. Okay, and halfway between 5 and 9 is 7. So these are going to add up to 28 because it's 4 times 7. Okay, so 1 plus 5 is 6, plus 9 is 15, plus 13 is 28. Okay, and that's really what's going on with this proof from Gauss, is that the numbers are evenly kind of spread. You've got a certain number in the middle where you've got an amount of numbers to the left of it, an amount of numbers to the right of it, and basically they kind of all even themselves out. You can pick that middle number and times by how many you've got. Hopefully that gives you a little bit of insight into the sort of pattern and the structure of arithmetic sequences. Let's move on and look at a much more generalised way of approaching this so that we can apply this to any sequence. Okay, and most of you should be familiar with the notation that we use the letter A for the first term of a sequence. Okay, and the definition of an arithmetic sequence is that we simply add some number, and we call that, or we use the letter D, well, D for difference, basically. If we now add D again, you get this, and if you add it again, you get this. Okay, and you carry on. Okay, and let's maybe imagine if I did this for 100 terms again. The important thing really is to realise that the last term, or the 100th term, would be A plus 99D. So in other words, when we get to the 100th term, we started with an A, and then we added D 99 times, not 100 times. That's really important. Okay, it's 99 times. And this basically gives you your formula for the nth term of a sequence, or sorry, an nth term of an arithmetic sequence. Okay, so the nth term is A plus, well, what we're really saying is we add, if there's 100 terms, we only add 99 Ds. So you can think of this as n minus 1 lots of D. So if there was 50 terms, the last term is A plus 49D. Okay, and it's really important to understand that this A plus n minus 1D is the last term, or it's the nth term of an arithmetic sequence, okay? Because we're going to need that in our proof. But what we're actually going to do is we're going to do exactly what Gauss did. We're going to just write that out and then write it backwards and add them together, okay? So I'm just going to use a little bit more notation here. Sn is the sum of an arithmetic sequence. So the first term is A, the second term is A plus D, but because we're doing a sum, I'm just going to put a plus sign in between these terms. So this is the first term plus the second term plus the third term. Okay, now I'm not going to obviously write them all out. But what I'm going to do is I'm going to jump to, well, the last term we know from what we just did is A plus n minus 1D. Okay, and maybe pause the video, think about what the previous term to that would be. Maybe just pause briefly, have a think, but it should be clear that it's n minus 1D. Okay, if you think about it, for 100 terms, the last one would be A plus 99D, that's 100, take away 1. The term before that is A plus 98D, Well, that's 100 take away 2. Okay, so now we're going to use Gauss's clever technique. We're going to say, well, actually, let's write these numbers backwards. So I'm going to put n plus n minus 1d, the last term, at the front. Okay, sorry, I don't want a comma there. I want a plus sign because this is a sum. Okay, so that next term is a plus n minus 2d. Sorry, don't need that little bracket there. And we carry on, and then at the end, as we get to the second to last term now is going to be the second term of the first sequence, a plus d, and the last one is a. Okay, so again, maybe pause the video and just make sure that you fully understand how I've written this out, because if you were going to do the proof in an exam question, you've got to get these two steps right. Okay, so once we've got that, we're going to use Gauss's technique of adding these together. Okay, now very important in terms of the technique for coming up with the proof is that I've kind of got two kind of like equations really, or formulas. So I'm actually going to start by adding the two left-hand sides of this formula together. I'm going to get two lots of Sn. That's the equivalent when I was talking earlier of when I got 10,100 for the sum of the first 100 numbers. We needed to divide it by 2 because we'd added it up twice. This is just a kind of algebraic way of representing that. Okay. The important bit is that we now need to add a plus n minus 1d. So I'm adding these two terms together. Now, the only thing you've got that you can collect together there are the two a's. Okay, so we get 2a plus n minus 1d. Okay. Now, it's not quite so obvious with the other terms, but they are all going to be the same. I will do it just for the next term. So the next term, we've got two a's again, okay, but I've also got to add a d on, okay? So I'm going to get 2a, and then if I've got n minus 2d, and then I add another d, it's going to be n minus 1d. It's easier, again, to see that as if I had 98d, and I added 1d, it would be 99 again, okay? So you basically get all of these same terms again. We just have to count up how many of them we've got. Now, in the example that Gauss did, he was adding up the first 100 numbers, so we times by 100. This technique is that we're doing this for the sum of n terms. So that's how many terms we've got, is n. So we just times here by n. And this basically is our formula, but it just needs a little bit of tidying up, okay? So I'll leave the 2 on the other side for now. Okay, I'm going to tidy this up by bringing the n to the front and just putting the 2a plus n minus 1d here. And hopefully this is starting to look, if you already know the formula, this is starting to look a little bit like the formula. And I'm going to cheat and save myself a little bit of writing here. I just need to get rid of this 2, so I divide both sides by 2. And this is your formula for the sum of the first n terms of any arithmetic sequence.